Hello class, welcome to the second part of 3.1. Here we attempt to provide a definition of a derivative using the idea of tangent lines. So here we have these objectives in this portion of section 3.1, and we are going to consider the concept of secant lines to develop into tangent line. We've seen this before, but a quick look at that. So your point of interest is P, which is A comma F of A. Okay. So our focus is to find the slope of this curve, right? This is the curve. To find the slope of the curve, we are trying to understand the slope of the curve at a point, and that point of interest is A. Well, the information we have so far is that if I had 2 points on the curve, then I can draw a line through it. As you can see, the orange line, I can draw a line through it and find its slope. That gives me the slope between those 2 points. It's not the slope of the curve, but it's the slope of the secant line that connects P and Q1, right? So if I'm only interested in finding the slope at A, not A to some other point, then the idea here is to keep getting that Q1, move that Q1 closer and closer to A. So from Q1, we move to this point Q2. Q2 is closer to A than Q1. And you find the secant line for P, from P to Q2, right? That's the line PQ2. So for that line, find the slope. That'll be a better estimate than PQ1, the orange line, because now you got a point that's closer to A. So if you keep doing this, you find another point Q3, let's say that was even closer to A, you find the slope of that secant line, and so on. You will reach a point where this Q point is actually coinciding or getting really, really, really close to the Q, so that it's as if you have just one line passing through that point instead of passing through 2 points. And that point, this orange point, point A, would become common to both the curve and the line that passes through it, becoming the tangent line at x equals A. And so previously we said slope, at A, slope of the tangent line gave us the instantaneous rate of change. Okay. Let me write that here. Instantaneous rate of change. At that instant, what happened, right? Of the function at x equals A. What we did to find that is also known as the derivative of the function at x equals A. So we're giving it a new view, okay? So we are looking for the slope of the tangent line, right, at x equals A. So we can think of the measure of the slope of the curve for this function at a given point as the rate of change in a particular instant, right? That's called the instantaneous rate of change. And now we are calling it as the derivative. Okay. So a derivative is, as you approach this point A from the left and from the right, what happens, right? So that's the definition of the limit. So we can find this value by finding the limit of the slope of a line that connects x equals A with a second point that is infinitesimally close to this point A, okay? So you are looking at another point that is so very close. Let me see if I can find another color. It's getting so very close to this orange point that it's almost negligible that it coincides with the orange point, right? So this is how we denote this instantaneous rate of change. Now recall that average rate of change was f of a plus h minus f of a over h, isn't it? So in other words, if I had, say, h distance away from A, right? That gave me Q1, Q2, and all that. So if I'm allowing Q to approach P and get closer and closer and closer to P, in other words, I'm interested in making this H very, very, very small, right? Because you want this A plus H to move closer and closer to A. So in other words, you are allowing H to get closer and closer to 0. Yeah. So this is an idea when you allow something to approach a value. That's the concept of limit, right? So we always say as x approaches a, what happens to the function? Likewise, as h approaches 0, what happens to the tangent line, to the slope of the tangent line? So then this gives us a new notation, f prime of a, that's the derivative at a, which is when you find the limit for the slope, right, function, as h approaches 0. Notice that when you plug in 0 for h, the denominator becomes 0, making it undefined. But we are not trying to do that. We are trying to use limit to understand how this works. And we've seen cases where we can handle this nicely. And this will take care of helping us find the derivative, f prime of a. So let me write a quick explanation here. This is a notation. So when you apply limit to the average rate of change formula, you get your derivative. So this is the derivative of f of x at x equals a, at a particular point. And we read it as, let me say, read as f prime, the f with the dash is called f prime. You could also have, instead of a plus h and a, you could have had just x and a. Well, it doesn't change much. You just will not have the h notation, but you will still have you would still take the limit. So f of x minus f of a over x minus a, and you want this x to approach a. So then your limit will change accordingly, so that you're trying to understand what happens. So if I come back to the graph here, so this was a, and instead of a plus h, I would call this x. So then I'm saying with this x is approaching a, right? As we get closer and closer to a, what happens? Or alternately, you could have had your x here as well. That's the case, then you're approaching a from this side. It doesn't matter where your x is, as long as it is a certain distance away from a and you're trying to reduce that distance to 0. Let's look at some examples here. Yeah, here we have the first one. Find the instantaneous rate of change of f of x, x squared minus 4x plus 1 at x equals -1. So instantaneous rate of change, another name for this is derivative. And the notation for derivative, it was f prime, and in this case, it would be f prime of x at x equals -1. That's what the instruction says. So then we are ready to roll with the formula. So let's write f prime of a, which is the derivative, right? Instantaneous rate of change is another name for derivative. So derivative is f prime of a limit. We could use x approaches a formula. All right, now we are looking at a particular a. In this case, our a is -1, because that is the particular point. your x is choosing that particular value. So f prime of -1, limit x approaches -1, f of x minus f of -1 all over x minus a is itself -1. So you have double negative in the bottom, which is, let me see if I can close this. Okay. Limit x approaches -1. F of x is x squared minus 4x plus 1. This is given to us. Minus, and I want to evaluate that function at -1. So -1 squared minus 4 times 1 plus 1 is what I plug in for x, all over x plus 1. So we have to do a simplification there. That gives us x squared minus 4x plus 1. Those are all numbers. There's no x in there, right? So that gives us 1 minus 4, which is, okay. Okay. So you have 2 minus 4 minus 2. This is a quick fix here. This was a -1. Okay, yeah, that fixes it now. That's going to be 4 plus 1, 5. 5 plus 1, 6. So 1 minus 6. Make it a minus 5. So I'm just trying to do all the calculation by the side so that I don't have to do it in one extra step. Okay. So if it helps, you can see that when you do the calculations yourself, this comes out as, what was it, 6. So plus 1 minus 6 is minus 5. All right, so in these cases, you'll have to factorize it, something that you learned in chapter 2. So two numbers whose product is -5 and whose sum is -4. X plus 1, x minus 5, okay, over x plus 1. So you know these cancel off, leaving us with limit x minus 5. Now you're ready to apply the limit. So plug in for x as -1. So -1 minus 5 gives us -6. So this is the instantaneous rate of change of the function f of x at x equals -1. The answer is -6. Okay. Let's find the derivative of a polynomial function. To find the derivative of the function f of x equals 4x squared plus 2x at x equals a. Notice here they use the language derivative, right? That's even more, it's better because it's a lot more straightforward. So you're going to find f prime, in this case, f prime of a, right? Because x equals a itself, they didn't give us a value for a. That's fine. We can keep that. It's going to give us an expression in a, which is fine. So let's quickly write the formula. Again, for variety, I'm going to use a plus h format. Instead of x and a, I'm going to do a and a plus h. So you have f prime of a is limit h approaches 0, if you're using the h notation, all over h. Yeah. Okay, so now we have no value for a, but we know that your x now is a plus h, right? So wherever x occurs, I have to plug in a plus h. This is crucial. So don't attach a plus h at the end of your function. So let me write it somewhere here by the side so that it's very, very clear. F of, I'm sorry, a plus h, that's what I wanted to write. A plus h is not this, where you just plug in for a and then attach an h. it is not, they're not the same. Because f of a plus h means this whole thing is now your x, right? So then f of a plus h means 4 times, that's your x, so x squared, plus 2 times x. So in the place of x, you now have a plus h, a plus h. Every time you have an x, you have to replace it with a plus h. So this is the correct version. So please be careful about that. This is crucial. Okay, so 4 times a plus h, the whole squared, plus 2 times a plus h, minus f of a. So now your x is replaced with an a. So 4a squared plus 2a, all over h. Now we are ready to expand this because it's just algebra at this point. So FOIL it twice, or you can use the a plus b the whole squared formula. So then this is what I get, 4a squared plus 8a plus 4h squared. Distribute, right? All over h. Okay. To know if you did this right, what should happen at the end is every term that does not contain an h in it will have to cancel off. This is crucial because you should be able to factor out an h from the leftover terms on the top, so that that h cancels off with the h at the bottom. Because if you didn't do that, then you have, when you apply the limit and h has to take the value 0, you will have an undefined condition. So this is an assured method where your terms without h will get cancelled off, and the remaining terms you can pull out an h. Let me fix this 2a here. Okay. So then we have 4a squared and negative 4a squared, positive 2a, negative 2a. Look at your other terms. They each have an h. That's good. Now we can pull out that h. Again, don't single out an h. You should always factor out an h. So you can also factor out a 2, but it's okay because of, there's one more step where we have to apply the limit. So I'm only focused on the h. So I have 8a plus 4h plus 2 all over h. There were only 3 terms left up there. So that gives us h canceling off with in the top and the bottom. So limit h approaches 0, 8a plus 4h plus 2. Now we are safe to apply the limit, which means in this case substitution for h is 0. So you simply have 8a plus 2 upon plugging in for h as 0. So this is your derivative. And notice that this is a derivative when x is a. So you are free to give any specific value for a to find that corresponding derivative. Okay, so that is the slope of the tangent line at that point on the curve. All right, so we saw one, this was an example for a polynomial function. How do we find the derivative for a rational function? As you can see, rational means you have a ratio. In particular, it's a ratio of 2 polynomials. So you have to compute your f prime because you're asking for the derivative. And then a is not a specific number, it is a general a. Okay, so we have to use, we could use the x approach, x minus a approach, but I think I personally like the h approach because of the built-in test, right? If you can single out an h, or rather, sorry, factor out an h at the end, and that h cancels off with the denominator h, you know you're on right track. So I personally like this technique. So let's go for this. Okay, let's start because it's a rational. I'd like to first get these terms simplified as if I can. F of a plus h is 4 plus wherever you have x, right? Put in those shells and replace your x with a plus h. Yeah, so that gives us 4 plus a plus h over 3 minus a minus h. Remember to distribute the minus. Okay. And f of a is where you once again have a function that was an x is now replaced by a, because in the place of x you have a. 4 plus a over 3 minus a. All right, so let's go ahead and use the formula. F prime of a is limit f of a plus h minus f of a all over h. Limit h approaches 0. Let me use what I have up here. 4 plus a plus h over 3 minus a minus h minus 4 plus a over 3 minus a. I know, it looks scary. Oh, we have algebra. We have this toolbox, right? That has algebra and trig techniques. We just need to know what the right tool we should use to overcome the situation, okay? So this is going to look complex, but it's actually tedious, not complicated, okay? So this is going to take more space, so let's kind of spread out here. All right, if you look at what the setup is a complex fraction, okay? A complex fraction means you have a fraction over a fraction. So you technically want to make this into a single fraction in order to simplify this. If it's a complex fraction, you simplify it by making it into a single fraction. So you just want one numerator and one expression in the numerator and one expression in the denominator. So as you can see, the denominator has no problem. You just have an h, but it's the numerator. And so let's focus on the numerator by taking the LCD, right? So the LCD is 3 minus a minus h times 3 minus a, right? And on the top, you're going to have 4 plus a plus h times this 3 minus a minus 4 plus a times 3 minus a minus h. That is just the numerator, right? All over h. You have to keep tagging that h. Okay, I'm going to start a little off here. All right, it's time to distribute. It's going to get crazy now. Let's distribute. I mean, there are many approaches. I've just chosen this way to do this. Meaning when I say many approaches, you will still do the LCD and all that. But, you could have not distributed the 3 minus a plus h, and waited for it to see if it cancels off in the end. So that is the only change you could have attempted. Anyways, this will be the most simplified form, so that is good. So we have 12. So track with me, okay? I'll just show for 1 so that it doesn't get too cluttered. And then you have, oops. Yeah, so you have 3 sets of arches going there. That's what I'm trying to track. So I'm doing the blue first. 12 minus 4a plus 3a minus a squared plus 3h minus ah. Okay, and do the same thing here. Oops, oops, oops. Okay. So you look at the arches, and that's how you know how many terms there will be, right? So in this first expression here, the blue, green, and the red, I have 2 of each, isn't it? So you expect 6 terms there. So 1, 2, 3, 4, 5, 6. So we have 6. Here I have 2 sets of arches, but then they are making, they'll count how many arches you have. 1, 2, 3 in the blue and 3 in the red. So here again, you expect 6 of them, but remember there is a minus outside. So as you distribute, you can take that into account as well. Okay, I can do it in one more step, but it's just going to make it lengthier. So we're just trying to do them all in one shot because we are in calculus. Okay, we are supposed to be mathematically mature to be able to do this. All right, so negative and 4 times 3 is 12. Okay, so that's going to be negative 4a, which makes it positive 4a with a minus outside. Negative 4h becomes positive 4h. Got those 3 terms. Then I have okay, 3a, so that makes it negative 3a. Negative a squared will be a positive a squared. Negative ah will be positive ah. All right, I got all of those. Again, don't worry about distributing the denominator here. Not yet. Okay. All over h. All right, let's get the ones that will cancel off, 12 and the negative 12. Negative 4a and positive 4a. Positive 3a, negative 3a. Negative a squared, positive a squared. Negative ah, positive ah. Ooh, interesting. we almost got rid of everything. We just have that one term because we really need something there, right? Otherwise, your derivative will be a 0. So it's good that we had the 3h and the 4h. And again, what's interesting is 3h plus the 4h, they are like terms. So you will be able to use, combine them. So 3h plus 4h is 7h over 3 minus a minus h times 3 minus a over h. That looks so much better, isn't it? Now what we do is, it's still a complex fraction because you still have the 3 layers there. You see the 2 division bars. Remember that there is a way to convert both the numerator and the denominator to both look like a fraction. This is essential because if you let me show a quick recall on what we did with numbers. Let's say you had 2 over 3 over, say, 5 over 6, right? How would you simplify this? We would have done this. 2 over 3, the numerator, times the flip of the denominator. And that gives us, you can cross cancel, 4 over 5. And you will employ a similar technique here. So I'll keep the numerator, which is a fraction, times the flip of the denominator. So h over 1 becomes 1 over h, the reciprocal. Okay? Again, remember the setup should be that your h's must cancel off. And that happens. Well, you still have an h in the denominator, but it's not serious where it's going to turn your denominator into a 0, right? In fact, in the next step, let me one more step and then. So we have 7 on the top over 3 minus a minus h times 3 minus a, right? I need more space, I guess. At this point, you can evaluate, apply the limit. So 7 over 3 minus a times 3 minus a, because when you apply the limit for h as 0, that goes away, so you have this. So technically, you have 7 over 3 minus a the whole square as your final expression. When you know a, you can find the derivative at that point A. As it stands, your expression contains an A in it so that it can be used for any substitution for A. And that is the derivative of a rational function. As you can see, the whole concept of calculus really was in getting that f prime of A. Once you plugged it in, it was pure algebra. So that's something you want to pay attention to and strengthen your algebra skills. So we saw derivative of a polynomial, derivative of a rational, and the last type would be finding the derivative of a radical. I apologize, it says rational here. Radical, because you have a radical. Okay. I originally wanted to do another example, but I found a good example for rational, so I didn't need to do another one. I'd rather do a radical. So we got that. Find the derivative of the function f of x equals 3 square root of x at x equals 16. It's a radical because you see the radical sign there. Right? Does the formula change? No, it doesn't change, but a few algebraic techniques will be kicked in because of the setup. Okay. All right, we will go ahead with, first identifying x equals 16. They gave us a nice number, not an a. So x equals 16 is your a. Your a is 16. So when they say find the derivative at x equals 16, they're asking us to find f prime at 16. We're asked to find f prime of 16. Okay. Now we have f prime of a, the general formula, right? Limit h approaches 0, f of a plus h minus f of a all over h. All right, so now we have h approaches 0. We have f of x is 3 root x. So in the place of x, I have to plug in a plus h. This being a simple one, I am doing the substitution right in the formula. Minus f of a. In the place of x, I now have to replace it with a all over h. Now, the technique that we used in the rational functions was to simplify the complex fraction by first doing the LCD, simplifying it into a single fraction on the top and turning the denominator into a fraction, and then did top fraction times the flip of the bottom fraction. That was the algebraic technique. Here we have radicals, so you can't do the distribution and all that, right? So you have to approach radicals using the concept of conjugate. Conjugate means, at least in English, it means that you, conjugal love, the intimacy, right? That's what it means. So the conjugal love between a man and a woman produces a desired outcome, which is an offspring, right? Likewise, in math, when you multiply a number by its conjugate, you get a desired outcome. In this case, that desired outcome would be to eliminate the radical sign and be able to obtain an expression without the radical sign. That is the desired outcome. So if I had a, for instance, I'll just say a plus b, its conjugate will be a minus b, right? So technically, a conjugate is equal and opposite to what you start, okay? So you have the same a and b, so the same players, a and b, they haven't changed. But one was a plus in between, the other was a minus. So they're equal and opposite in sign. So if I had square root of a minus square root of b, its conjugate will be square root of a plus square root of b. The players a and b, the square root of a and square root of b will be the same, but you do this. And the process of conjugation is where you multiply them together. And when you do this, you multiply, you don't add them or you don't do other things. You multiply them, and what happens is this effect will, you have to FOIL, okay? Or you can see it as difference of squares. That's an easier way, actually. So you have square root of a times square root of a, which is square root of a squared. minus root b root a plus root a root b minus root b the whole squared. And as you can see, these cancel away. Square root of a the whole squared is simply a. Square root of b the whole squared is simply b. And you can see that the end result was the desired outcome, which eliminated the radical for us. So you multiply these two expressions, an expression and its conjugate, to be able to get the desired outcome. So that is the technique we're going to use when we deal with radicals. So limit h approaches 0. 3 times, again, your h in the denominator is pretty simplified, so you really have no business dealing with that until the last step. So you are technically multiplying up and down by the conjugate, because that's how you'll balance it, right? So conjugate, remember, equal and opposite. So 3 times square root of a plus h and 3 times square root of a. These are the players. In between you had a minus, so you're going to have a plus here. And what you do on the top, you do to the bottom as well to preserve the balance. All right. Once you've set this up, go ahead and FOIL the numerator. Again, I showed you how to FOIL it in the side example. So here I'm going to go use difference of squares to kind of give you a variety on techniques that we can employ. So limit h approaches 0, a squared minus b squared, right? A plus b times a minus b is the format that you see. So this will be a squared minus b squared. And that's kind of what you'll get if you did the FOIL as well. So if you want to do the FOIL, go ahead and see that you'll get back the same thing. Now in the denominator, we do not want to distribute the h to these terms because we anticipate the h to be cancelled off. You can put the dot, or I think this will be better if I put a parentheses. Okay, so let's take a look at the numerator. So that's going to be 3 squared, which is 9, times square root of a plus h the whole squared, eliminates the square root. That was the whole idea. Minus 9 times a over h times 3. Okay, now we're ready to distribute on the top. Oh, went too far. Okay. H approaches 0. 9a plus 9h minus 9a over h times 3 square root of a plus h minus 3 root a. You can already see how it's all set up, right? The 9a and the minus 9a will go away. You can also see that your leftover term is 9h, and you have an h in the bottom. You don't have to do it in 2 separate steps because I can rely on your mathematical maturity. I believe that you can understand that I'm doing 2 steps in 1 with the understanding what leads to the next. All right, so the h's will go away and you're left with the 9. And we can kind of also do one more step right here. So you have the 9 on the top, and you can apply the limit because your h's were cancelled off. 3 square root of a is what you'll have here, minus 3 square root of a, right? The a plus h, yeah. I'm sorry, not the minus, you have the plus. That would be dangerous, right? If you had a minus, they would cancel off. All right, so 3 square root of a plus 3 square root of a. So these are like terms. So that will be 2 times 3 square root of a, which is 6 square root of a. Watch out for your 6 and your a and your 9. You know, write them very clearly because your 9 and your a can begin to look alike. You have the 3 and then you have the 2, right? 3 cancels them both. So that leaves us with 3 over 2 root a for our f prime of a. But remember, that was not the question. So let me write that out here. F prime of A is 3 over 2 root A. We were given A to be 16, right? Because by the time we forget what the problem was, so take you to the starting point. Look at this. It says find the derivative at x equals 16. So we come down here and we make sure that we answer the question when A is 16. So it's 2 square root of 16. Square root of 16 is 4. So 2 times 2 is I hope I'm doing this right. Okay, 2 times 2 is 4. For a moment, I thought it was a 9. The square root of 9, not square root of 16. I think I just was looking at something. Okay. All right, so you have f prime of 16 coming out as 3 over 4. So then we were able to come up with a definite numerical answer because your A was given to be at a specific point. A was 16, so we got this. So this is, I could call this as the general derivative for f of x equals, what was it, 3 square root of x at x equals a. And this was derivative for f of x equals 3 root x. Let me write that again. 3 root x at x, at a equals, or x equals 16, where your a was 16. And that is how we find derivative using limit of the slope, or limit of our rate of change. I hope this lecture was useful to you. I'll see you in the next part.